have you ever stopped to think about how the electricity from your wall socket, which is pretty chaotic, gets turned into the smooth, stable power your phone or laptop actually needs? Well, that whole journey from messy alternating current, or AC, to clean direct current, DC, is exactly what we're going to break down right now.
Electro Knowledge. Power up your concepts.
In this diagram, it lays out our entire roadmap perfectly. We start over on the left with that wavy AC input. First, it passes through a rectifier, which kind of forces it to flow in just one direction. Then, and this is our main focus today, it hits the filter circuit, which smooths out all the bumps. And the result? That clean, flat DC output on the right that our electronics absolutely depend on. This is how we're going to tame that wild current.
So, here's how we'll tackle it. First, we've got to understand what we're up against, the unruly ripple problem. Then, we'll meet our filtering toolkit. After that, we'll build our first line of defense with a simple capacitor filter. Then level up with some more advanced combination filters. And finally, we'll connect it all back to why this matters in the real world.
Okay, so let's dive into the problem. Because once you really get a feel for what pulsating DC is, you'll see why these filters aren't just a nice little add-on. They are absolutely essential.
The first step in this whole process is the rectifier. Its job is pretty simple. Take the AC, which flows back and forth, and make it flow in only one direction. It basically acts like a one-way street for electricity. But, and this is a really big but, the output is not the pure, flat DC we're looking for. Not even close.
So on the left here, you can see what comes directly out of the rectifier. See how it's not a nice flat line? We call this pulsating DC. Sure, it's all flowing in one direction, but it's still full of these bumps and valleys. And this kind of choppy, fluctuating power is just no good for sensitive electronics. It can cause them to perform poorly or even get damaged over time.
And those unwanted bumps? Well, they have a name: ripple. It's basically the leftover AC component that's still messing up our DC signal. You can think of it as electrical noise that we desperately need to cancel out.
So how do we actually measure this bumpiness?
We use something called the ripple factor. It's basically a grade for how much ripple is left in the signal. A high ripple factor means you've got a lot of fluctuation. A low ripple factor means a much smoother, cleaner DC output. The entire goal of a filter circuit is to get this number as close to zero as humanly possible. All right, now that we know the enemy, ripple, let's meet the heroes we're going to use to fight it. You know, our filtering toolkit is surprisingly simple. It really just relies on two fundamental electronic components. Meet the inductor and the capacitor. Now, they work in different but really complementary ways. An inductor resists any change in the current. You can think of it like a really heavy flywheel. It's hard to get it spinning, but once it's going, it wants to keep a nice, steady speed. A capacitor, on the other hand, resists any change in voltage. It's more like a small water tank that can absorb any sudden surges and then release water during dips to keep the pressure steady.
Okay, let's put these tools to work. We're going to start with the most common and straightforward approach, the simple capacitor filter. Just think of it as our first line of defense against that nasty ripple. Here's the circuit, and it is beautifully simple. We just take our capacitor, which is labeled C here, and we place it in parallel with the load. And RL is just the technical term for whatever gadget we're powering. This exact placement is the secret to how it all works.
It all comes down to a really simple two-step process. So, as the pulsating voltage from the rectifier rises up to a peak, the capacitor charges up, kind of like our water tank filling up. Then, as the rectifier's voltage starts to drop, the capacitor starts to slowly release that stored energy to the device. It effectively fills in the gaps between those voltage peaks. And the result is a massive improvement. Those really deep valleys we saw in the voltage before are now much, much shallower, which means the ripple factor gets reduced significantly. Now, for a lot of simple applications, this is perfectly fine, but for more demanding electronics, we can do even better. So how do we level up? Well, we start combining our tools. By using both inductors and capacitors together, we can create filters that are way more powerful and effective for those tougher jobs. Here are two really popular combination filters. Over on the left, you've got the LC filter, which pairs an inductor and a capacitor. And on the right is the pi filter, which gets its name because its diagram kinda looks like the Greek letter pi. The key difference here is that the pi filter adds a second capacitor for even more smoothing power. The pi filter is so effective because each part has a very specific job. First,
That input capacitor, C1, gets rid of a huge chunk of the initial ripple. Then, the inductor in the middle acts like a gatekeeper, blocking almost any remaining AC from getting through. And finally, that second capacitor, C2, does one last smoothing pass, giving us an incredibly clean DC signal. It's a really powerful three-stage cleaning process.
So which filter is the best one? Well, as you can see from this chart, it really depends on the job. A simple C filter is great for light loads, maybe like a small LED circuit. An L filter, on the other hand, works better for heavy loads that draw a lot of current. The LC filter is a pretty good all-rounder, but if you want the absolute highest ripple reduction, which is perfect for sensitive, high-voltage gadgets, the pi filter is the clear winner.
All right, let's bring all of this home. We've been talking about some pretty technical ideas, but it all comes down to one simple thing: making sure the gadgets we use every single day work the way they're supposed to and last a long time.
And so we come back to our original map, but now we understand every single step of the journey, don't we? We've seen how to take that chaotic AC sine wave, rectify it into a pulsating DC, and then use our filtering toolkit to smooth out all that ripple, delivering the clean, stable power our devices need to thrive.
And why is this so critical? Because not filtering the power has real, tangible consequences. High ripple can introduce that annoying hum you sometimes hear in audio equipment, it can cause components to overheat, and ultimately it can lead to them failing way too early. This whole process is absolutely fundamental to the reliability and longevity of our electronics.
And that leaves us with a final thought to chew on. As we keep pushing for our devices to be smaller, faster, and more powerful, the challenge of providing clean power just gets tougher. I mean, how do you cram high-performance filters into these tiny little packages without them overheating? That's the exact challenge engineers are tackling right now.
Thanks for watching. Like, share, and subscribe to Electro Knowledge for more electrical concepts.